thinking about intervals of increasing and decreasing and everything that comes along with that. So just generally thinking about when a function is increasing and decreasing. All right? If we were to just draw some crazy function over here, notice that when it's increasing, literally as we move from the left to the right, when it is increasing, we know there has to be a positive slope. Okay, so it's really crucial. We just have that fundamental idea right there. If our function's increasing at any time, at any of these moments, at any of these instances, at any of these instances, the instantaneous rate of change, the slope, is positive. Notice right there, anywhere, even right here, it's getting close to changing, but it's still increasing. It's still increasing right there. And so all of these slopes are positive slopes. And a positive slope is saying our derivative is positive. Our derivative, our slope at these moments, our instantaneous rate of change, I'm saying a lot of words that all mean the same thing here. Our rate of change, our slope at all of these moments is positive, and we can visually see that makes our function increase. The outputs that we're getting out from the original function are getting larger. This one's at 2, and then we're at 3, and we're at 4, 5, 6, 7. And then it almost gets to the y value of 8. But then right here, think about the tangent line right here. It would have to be a horizontal tangent line where the slope at that moment is 0, and then we get these negative slopes. The negative slopes are making our function decrease. We're seeing visually our function is decreasing right here until once again we get to a 0 slope where the tangent line would again be horizontal, and then we again see it has changed from decreasing to increasing. So over here, our instantaneous rates of change would all be positive. So there's a lot right there that we can continue to add on. Notice that when we changed from increasing to decreasing, at this point right here, where we went from increasing to decreasing, because this point exists, it is a continuous function where we have gone from increasing to decreasing. That point right there is a relative maximum. And we can see that. I mean, we could have picked these out from the graph just based on our general pre-cal knowledge, but even if we didn't have the graph, knowing it's a continuous function that has changed from increasing to decreasing, we are guaranteed to have a relative maximum at that point. That point exists. Down here, this point right here where we had our horizontal tangent line, notice this is also a special point because we have now gone from decreasing to increasing. We have a continuous function where we have changed from decreasing to increasing. And what is special about this point? This is a relative minimum. And I know the way in which I drew this function, this is, if this is it, if this is the domain we're looking at, this is the absolute max and that's the absolute minimum. But When we're just looking at changes from increasing to decreasing or vice versa, we're looking for relative extrema. Because just changing from increasing to decreasing, we're not thinking about the wider scope of the graph. We're just thinking about what must be happening if this is a continuous function that's changing directions. And we call this idea the first derivative test. The derivative is telling us if our function is increasing or decreasing, and if we can see those changes, then we can determine if we have relative extrema.